just so I've got kind of this GPA omitted variable. I think the one I uploaded for this class, we just had the sheet 1 there. If you have the other sheets, just ignore those for right now. We're just going to kind of use this sheet 1, which has this data set that has a bunch of college student GPAs. It had what their SAT score was, whether or not they're student athlete, all these other things. Okay. Well, one thing we might be interested in, like a question that you could think about is being a student athlete in college, does it have a detrimental or does it have a beneficial impact on how you perform during college? So the story goes, being a student athlete takes a lot of additional time. I remember when I was an undergrad, there's this econ major who was on the football team. I think he was the long snapper. And he would like explain to me his week. And it was like, how do you find time to do anything? Like they had like film every day, like weight room, but also practice. Like it was just booked all day, right? So you have a much busier schedule, but at the same time, would have helped me probably to be in something a little more structured like that when I was 18 going to college, because it gives you a lot more time management skills, right? It teaches you very quickly how you manage your time. So maybe it has a positive effect, maybe it has a negative effect, right? So we might go, okay, all right, let's look at this data and let's run a regression. And we're going to think about maybe college GPA, so that's going to be our Y variable, depends on whether or not someone's a student athlete. So we'll use this 1-0 variable that identified was the college student and athlete or not. We've selected the labels, right? Hit OK. Okay. So now when I'm looking at this output, we've got a couple new things that we can actually look at. Right? First of all, what percent of the variation am I explaining, or what proportion of the variation am I explaining in the variation GPA by simply that student athlete variable? 0.008, so 0.8% of the variation. So not very much, right? It's a very small piece of the pie, right? There's a lot of other things that probably are a lot more useful, like probably the person's SAT score or how many credit hours they've taken in college so far. But we do start to see that R squared is there, okay? Now, for this class, we're not going to use the multiple R, the adjusted R squared. Those are some additional kind of topics that we would kind of talk about if we had another month or so. But for us, we are going to use that R squared now, okay? I then go down and I look at these coefficients and my p-values, and I say, well, look, that student athlete variable, it looks like if I have a 1 unit increase in it, which is a 0, 1, so going from the 0 to the 1. So not being a student athlete to being a student athlete would predict my GPA goes down by 0.28 points, right? Which in the context of GPA, it's a pretty sizable effect. Right, on a 0 to 4 scale, a reduction of 0.28 is pretty large. And that p-value, when I see these e to the negative 0.9, that means move the decimal 9 places to the left. So this is 0.8 zeros and then a 4, right? This p-value is basically 0. Anytime you see e to the negative in Excel, that basically means 0, okay? So if my p-value is basically 0, right, if we remember what we said earlier, is the null is that the relationship is always 0. So I'm thinking about predicting GPAs using whether or not this person's an athlete. I'm assuming that relationship is 0. I just found a p-value that's approximately 0. So that's going to be less than alpha, no matter what level of confidence I want to do, right? So with like 99% confidence, I could reject this null, right? And say that there isn't no relationship, right? Or think about what we start out assuming is that there's no relationship. So I can reject that, right? Because my p-value is less than alpha. Or I found significant evidence that there is a relationship, okay? At least I can say that with 99% confidence, right? Because my p-value is very, very low. Any questions over anything I said there, or about the concepts? Want to hear something said again before we keep moving? Okay with this? All right, so what we would typically say, we speak a little bit different when it comes to linear regression. So like I said, you can kind of think about like my alphas, so like 0.01, 0.05, and 0.1. The significance levels would be 1, 5, and 10%. And that's typically how coefficients are discussed, right? They kind of have corresponding confidence levels, right? 99, 95, and 90. But we generally don't say that when we're talking about slope estimates. I'm not, to get into the nuances of why, it's not overly important for this class, but we generally say things are significant, and we kind of use these significant levels. So here I would say with a p-value of basically 0, that coefficient estimate on a student athlete is significant at the 1, 5, and 10% levels, okay? Or I can reject at all those levels. So we go back here. We might go to the university and say, look, you should shut down all your athletic programs, right? You're hurting your student at your academic performance, right? But there's likely a lot of things that are correlated with being a student athlete, like especially if this college set comes from D1 universities, right? When we look at the data, we definitely see, for men's basketball and football programs, colleges are definitely a little bit more lenient on the academic kind of standards for their student athletes relative to their student body, right? So go back and say, okay, well, do I have some measure of the intellectual ability or incoming intellectual ability of these students? Well, it's not perfect, right? Some people aren't great at taking tests, but it's a decent measure, right? It's some measure that we can use. So we'll use that SAT score variable, right? So simply by including that SAT score variable, so all I do is select both the variables I want, Control Shift or Command Shift on a Mac, hit the down arrow. Now I'll run this regression again. Now we'll see, by including GPAs, I increased my R squared to 0.16. So I'm now explaining at least about 16% of the variation that exists in GPAs. And if I look at that coefficient on athlete, it's fallen from -0.28 to -0.05. Right? So it looks like it's way less detrimental to be a student athlete in, on your academic performance. And what's more, if I look at this p-value of 0.26, can I actually say that this is statistically any different from 0? Well, I can't at a p-value of 0.26. Right? Is that going to be less than even an alpha of 0.1? No. So I'm going to fail to reject the null. If I fail to reject the null, what I'm saying is, based off the sample evidence I have, I can't say that relationship between GPA and being a student athlete is anything other than 0. Right? And that was simply because the correlation of that one variable, SAT score, right? By omitting that variable, I was biasing the estimates that I was seeing. But once I included it in my regression, I kind of eliminated that bias, right? So go back here. We could also interpret the SAT score variable, and it is highly significant, right? This p-value is very, very close to 0. So, right, e to the -159 would mean move the decimal point 159 places to the left. This is basically 0. So how would I interpret this SAT score variable? Remember, we always do a 1-unit change in the X variable causes my predicted Y to change by whatever that coefficient is. So how would I interpret that? What would a 1-unit increase in the SAT be? One more point on the SAT score, right? So my units for the SAT score, just the points that I'm earning in the SAT. So one more point on the SAT score would predict that my GPA goes up by 0.00, about 2, or 0.0019. And that might seem really small, but 1 point on the SAT score is really small, right? So it's maybe a little bit more useful to be, well, what if I get 100 points more on the SAT score? Well, if I know the effect of 1 point, how do you think maybe I could get the effect of 100? Simply, yeah, right? So I could say, take that coefficient that shows me the effect of 1 unit, multiply it by 100. Okay, now this makes a little more sense. If someone went from like an 1100 to a 1200 on the SAT, we would predict their GPAs would be about 0.2 higher. And that sounds reasonable, right? It's not the largest effect, but it's, on a 0 to 4 scale, it's not nothing either. Okay? Any questions on that? Start and hopefully to maybe see some of the usefulness of what we can do with these linear regression results. Where are we at in time? Okay, so the other thing I wanted to show you here is if we go back to that data on sheet 1. Well, I've got a lot of other variables in here that look like they might help, or or might be correlated with being a student athlete as well. So let me just throw the kitchen sink at this, right? So I go to my regression. I still have my Y variable GPA selected, so that's good. My X variables, I'm just gonna include everything, right? And for now, don't worry about this SAT squared term. I might show something to you next week that kind of talks about this, but for now, just know that it could be another useful kind of right-hand side variable. So I'm gonna include everything I've got in my data set and just try to control for as many things as possible, right? So actually, I didn't select everything though, I just pointed to it. So I'm gonna select from SAT to SAT squared. I've got my label selected, hit OK. Zoom in so we can see this. Well, now notice I can explain about 30% of the variation, right? And that makes sense. If I'm just including more factors on that right-hand side, I can probably explain or more of the variation or come up with better predictions. Right? And then go down here. I've got a ton of different coefficients. I've got a bunch of different p-values. If I go through here, I can very quickly say, okay, which of these variables can I say have a significant relationship with GPA? And let's say we want to do it at the 90% level, so an alpha of 0.1. Well, basically what we would do is go through every single variable's p-value, and if it's less than 0.1, then we would reject the null. Remember, the null was that there's no relationship. So if we can reject the null, what we're really saying is we found evidence there is a significant relationship between these variables. So we go through, the intercept is significant, SAT score, athlete, verbal math, everything here is significant. Oh, looks like race, right? Kind of doesn't impact as much, kind of the being white or not relative to, you know, the other, we only kind of include 2 racial groups here, but if we had more information on this, you know, we could kind of create indicators for every single possible one, any demographic we want really. Total credit hours has a significant effect, high school size, and then that squared term also. So everything in here looks like it's pretty helpful at explaining the variation in GPA, right? So most of almost all but one of these was a significant, you know, we could reject the null, okay? But what we really want to focus on now is once I control for all these other factors, now look at what happens to the coefficient on student athlete. We actually now, going from being a non-athlete to an athlete, looks like it actually improves GPAs by about 0.12 points, and it's significant at even a 99% level or the 1% significance level, right? So starting out with a very naive regression, we might think, okay, being a student athlete is really bad for the student's academic performance. As we add in additional controls, we eventually see, well, no, that student athlete coefficient was really just picking up the negative effects of all, you know, these other things that it was correlated with, right? That they maybe tended to come in at a lower intellectual level or ability level, right? Kind of trying to pick that up with the SAT score. Maybe some of them might be taking more credit hours or less credit hours, or whatever those relationships are. So once we account for them, what we now can say is 2 students who have the same SAT score, got the same score on this verbal math test that they were using, have the exact same rank in their high school. We're either both male or female, we're either both white, black, or kind of some you know, other minority group. Both have the same total number of credit hours, both from the same high school size. Well, if they have the same SAT, they'll have the same SAT squared. All of that is exactly the same, but one of them is a student athlete, then their GPA would increase by 0.12. That's a lot more powerful of a statement than the naive regression that we started out, right? So, you know, using this linear regression tool really is way more powerful probably than anything we've done in this class so far, right? Because most of the other things we've looked at, it was very hard to control for other factors. Go back through how we did that final one just to kind of see it again. So hopefully at this point, we have that data analysis added in. If not, we go to options, add-ins, manage the add-ins, make sure the analysis tool pack is there. On a Mac, like I said, if you go through the tools bar and you see add-ins and you make sure that this is checked, right? So once that's checked, we can go to this data tab, go to data analysis, scroll down to regression, hit OK. So our Y variable, we were trying to predict GPAs, right? So we select college GPA and select the entire column. Just Control Shift or Command Shift on a Mac and hit the down arrow. Then for our X variables, we're just going to throw the kitchen sink in. So I'm going to include everything over here on the right-hand side. Okay. So Control Shift, hit the down arrow. I selected my label, so I make sure that box is selected. I hit OK. And I get my output. Right? So we kind of went through that last class, if I recall. Right? We looked at the effect of being a student athlete on GPAs. We then added in just the SAT measure as an additional control variable. And then we said, what if we added in everything? Okay. So is this looking familiar? We're up to speed at this point. Okay. So we're going to zoom in here so I can see this a little bit better. But using this output, right, we can pick up a few things. So this R squared, right, that's going to tell us the percent of the variation in this original Y variable that we're explaining with all those variables we include on the right-hand side. So we're doing a decent job, right? We would like this to be really close to 1, but at this point, we're explaining about 30% of the variation in GPA, okay? We then have all these variables we could start to kind of interpret the coefficients on them. So for instance, on SAT, we said for every 1 point increase in the SAT score, the predicted GPA would actually go down. However, this is going to be a little bit weird because something I'm not going to expect you to know how to do is I included a squared term. So this is going to pick up if there's some quadratic relationship with SAT scores. So this might look not intuitive, right? But it's because the total effect of a 1 point increase in SAT, right? If SAT goes up by 1 here, it's going to impact this variable as well. Right? So you can kind of imagine if I had written out my regression equation, and I'll kind of shorthand it here, but so GPA will have some intercept, I'll have SAT. And let's for now say I include this SAT squared, athlete, all these other variables, right? Well, I can come up with the kind of total effect of a 1 point increase in SAT score. But notice if SAT goes up by 1 here, GPA would go up by beta 1. But also if it goes up here, right, a 1 point increase here is going to impact the coefficient as well. And what ends up being true, right, if we take a kind of derivative of this function in respect to what's changing, so right, the change in GPA from a change in SAT, we're going to get this guy here. Now, I'm not going to expect you to know how to do that. I'm just mentioning it because it's there in the output. And past this course, you could pick up these nonlinear relationships, right? So maybe it looks, I think actually what data looks like is something like this, so that the line of best fit would look something like that. Okay. Now, kind of punting on that, right? I'm not going to expect you to know how to understand these nonlinear relationships. We do need to understand that we can make predictions using this model. Okay. So to avoid the SAT squared, I'm going to rerun this and just run it without that. I just wanted to make you aware that that is a possibility. And since it was in the data set, well, let's just run it now and force that relationship to be linear. Right? So I only include up to the variables right before SAT score squared. We'll zoom in. Okay. So now if I'm looking here, it looks a little bit more like we would expect. A 1 point increase in my SAT score would predict that my GPAs, or my Y variable, goes up by 0.001. Okay. Now that may seem small, but that's the effect of 1 more point on the SAT. That shouldn't be that much more predictive. What if someone scored 100 points higher? Well, if I know the effect of 1 point, we said the effect of 100 I could just get by multiplying this by 100. Right? So I can scale this up to whatever level I want. Now, if I think about somebody going from a 1100 to a 1200 on the SAT, that would predict their GPAs are about 0.16 higher. Right? Not the largest effect, but right, we got a Y variable that only goes from 0 to 4. Okay. So with that idea in mind, once we obtain all the values, for these coefficients, I could then, all these would be numbers, I could take a hypothetical person, plug their values in for the X variables, and come up with what their predicted GPA would be. So for instance, if I had like a really simple linear regression, and let's say, I don't know, I run this, oops, sorry. I run this regression and I get, I don't know, 1.2 plus 0.002 times SAT, right? Let's say I just run this really simple linear regression. I could come up with predictions about the GPA by just plugging in different values for SAT scores, right? Somebody who gets 1,000, right? Well, this would be what? Move the decimal point 3 places. So 1.2 plus 0.002 times 1,000 be 1.4, right? And that's kind of the idea of how I would make these predictions. So it's more complicated because I have more variables, but this is generally how I would say to go about making a prediction for a hypothetical person. So we'll call this hypothetical person, right? So let's say this person got a 1,200 on the SAT. They were not a student athlete. They scored a 0.7 on this verbal math test, which I believe ranges from 0 to 1. It kind of represents the proportion of questions they got correct. Their high school rank was maybe they were 15th. Let's say they were female. They were not white or black, so another minority group. They've currently taken up to 46 total credit hours. And this high school size variable was a weird one. I think it's in the thousands, if I remember correct. So like it's in the hundreds. So I think like 9.4 would be 940. So we'll just choose something that's kind of within this range. So we'll go 4.00 just to keep it easy. So let's say their high school size, like I said, I think this represents 400 students. Okay. So I've got this hypothetical person. How could I come up with their predicted GPA? Well, probably the easiest way to do this would be just take each coefficient, multiply by the X value for this person. Now, for the very first row here, we've got the intercept. Well, when we're writing out this equation, right, the intercept isn't multiplied by anything. It's always added in to our prediction. Okay. So if I'm doing this in Excel just to save myself some work, I'm just going to put a 1 in here, and that way the intercept always gets multiplied by 1 and added in, right? So nothing crazy there. So I then go through and take the X value for this hypothetical person, multiply it by that variable's coefficient, okay? I'm then going to do that for every single variable. Now, essentially what I have here are all the combinations of the coefficient multiplied by whatever that hypothetical person's X value is. Every coefficient multiplied by that hypothetical X value for this person, okay? So the next step is I just need to add them all up, and that should give me my predicted GPA. So how can I do that in Excel? I'm just going to use that sum function and add up all those coefficients multiplied by the hypothetical X value for this person. Or I should say the X values for the hypothetical person. That's how I should say. Okay. So this person's predicted GPA would be 3.26. So what you can do, sorry, first of all, before I keep going, are there any questions on that? Or keep moving here. So this is how we would use regression output to make predictions, right? Once we have those coefficients, you're just plugging in the hypothetical person's X values and you can come up with what their predicted GPA would be. Yeah.
Could you say again which one was the intercept?
Yep. So if you go up to this very first row, right, we've got the coefficient on the intercept. The way that I just wanted to be able to drag this down, like I could leave this off, add these all up, and then just remember, I also have to add in that coefficient. Where was it? For the intercept. But I think that probably an easier way to see, I get the same value. I think the easier way to set it up is just put a 1 in there. That way it's like, just multiply the intercept by 1, and that makes sure that you're just kind of always adding it in. So multiply that coefficient by 1. That way we're making sure it always gets added in when we just take the sum of all these. Does that make sense? Yeah. That's a good question. Any other questions? We'll keep moving here. Okay, so one thing I could do, or could be asked, is if I look through these variables and say, which of these are, or which of these have a significant relationship with GPA, right, at the 10% significance level. So what I'm saying there is, when I look at these coefficients, I always start out with the same null hypothesis for every coefficient, which is that whatever that slope is, right? Maybe it's, the slope on the third variable, the slope on the fifth variable, whatever it is, we always assume that the relationship doesn't exist, right? That there is not a significant relationship between that x variable and our y variable. If we can find a p-value that's less than alpha, we can reject the null, which means we're rejecting that there's no relationship. Or said differently, we're suggesting that we found evidence that there is a relationship. So what we would say, like at the 10% significance level, where alpha is 0.1, we would then say for every variable that has a p-value, for every coefficient estimate that has a p-value less than 0.1, we would say there is a significant relationship, or we can reject that there's not a significant relationship. So we'll go through our variables. I'll kind of show you a kind of a neat way to do this. I'm just going to insert a column here. So we can use something that I showed you a little bit with hypothesis testing, but we can use this if statement. So what I can do is actually make a rejection decision pretty quickly without like having to look at these and maybe make a mistake. And I'll show you how you can maybe make a mistake here in a second. And just say, look, if this coefficient estimate, if it has a p-value that's less than, and actually, I'm going to actually use this cell right here. I'm just going to put my alpha value up there. That way, if I wanted to, I could change it. Okay? So if it's less than, well, let's do that first so it makes a little more sense, right? So let's say I put my alpha value up there. And then I say if the p-value on this coefficient estimate is less than that alpha value, comma, put the word reject, if that's true, comma, if it's not, just put the word fail, right? Or fail to reject if I really wanted to make this a little lengthier, okay? So once again, that if statement makes life a little bit easier because now when I drag this down, although if I drag this down, what do I have to make sure I do? Yeah, I want the p-value to keep updating to the next coefficient, but I'm always using the same alpha value to check against or the same kind of significance level. So I'm going to freeze that cell reference, okay? Now when I drag this down or I could drag it down, or if I get this black plus sign, if I double left click, it fills it down to the very last point of data. So either way, I quickly get my rejection decisions, right? So everywhere where I see a reject, I'm actually saying that there is a significant relationship, right? Because I'm rejecting that there's no relationship. So if I wanted to even make sure that I don't forget that, I could say that significant or not significant. If this isn't true. Okay. Maybe that way it's a little bit easier. So I copy this down, maybe all the way though. So it looks like everything except for that verbal math test and the indicator on whether or not the individual is white, right? Everything else I would say has a significant predictive power about GPA, or it has a significant relationship with GPA. Now I could do this by hand, like so when it comes to that final Excel homework that's up there, I can ask you to do a similar thing. You can go through and just tell me, I can reject these variables because the p-value is less than whatever the alpha is. But if I'm looking through this, a lot of times I see this mistake, I mean, a lot. You look at this and say, well, the only ones that are significant would be the black indicator variable, and that's it. Well, no, all these e to the negatives means move the decimal point that many places to the left. So anywhere where you see an e to the negative, those are all significant as well, because those p-values are basically 0. Okay. Any other questions other than that? Or sorry, other than that, on that. So you can go through and do it by hand, but here, right, Excel is kind of treating these as really, really small values. It doesn't make the mistake just looking at it, right? And we should even remember p-values, right, should be somewhere between 0 and 1. So if I see a 5 e to the negative 18, there's no way my p-value can be 5. It must be that I have to move the decimal point a certain number of places. Okay? So we would say that, all of these, the vast majority of these variables that we included have a significant relationship with the exception of 2. Now, when we're making our predictions, even though those aren't significant, right, we still use them in making our predictions. Right? it's still that they're valuable estimates. It's just that we can't say at a certain level that they're statistically or significant, or they're statistically any different from zero, right? Maybe we could if we got a higher sample size, right? I think we talked about maybe a little bit last class. I might be mixing up my classes here, but when we're calculating the test statistic for all these coefficients, it's just take that coefficient estimate and divide it by something called the standard error. Well, that standard error is very similar to what we were doing before when we had sample means and assumed true means. Just remember here, our assumed true coefficient value was always 0. What we divided by was the standard deviation of our sample means before. So the standard error, if you want to think about it, it's kind of like the standard deviation on those sample coefficients. Remember, these coefficient estimates we get from Excel are still coming from sample data, okay? So that's kind of what we're doing. And just like the standard deviation of sample means, this standard error, what was it? Take my y, predicted y's, subtract. I can't actually write this out for you. So it's like you hold the other things constant. Don't worry about this for right now. But all we need to know is that there's a sample size in the denominator, right? And so that if I increase that sample size, right, it's going to decrease that standard deviation, increasing my test statistic, decreasing my p-value. So having higher sample sizes, even if I see the same coefficient estimate, it's going to drive down my standard errors and kind of increase my test statistic and then decrease my p-value. Now, I won't make you